So the last two sections we're going to look at this week are 8.3 and 8.4. They both focus first on learning how to write complex numbers in what's called trig form. And then once you get it in trig form, it makes certain things with complex numbers very easy to do. Things that we used to have to use FOIL for, like if you had something like this, and I asked you to multiply those complex numbers together, the old way you had to do it would be go 2 times 4, 2 times negative 5i. Okay, you're doing all this foiling, and then you got to remember that positive times negative is a negative, 3 times 5 is 15, I times I is I squared, and we got to remember what I squared is. Does anyone remember what that is? Yep. Negative 1. So what basically would happen is that would disappear. That turns into a plus. 15 and 8 gives me 23. Negative 10, positive 12 gives me 2i. So if you wanted to multiply on that, that's how we do it. The old way. Dividing, that was a little bit more of a pain. To do division of complex numbers, we had to multiply by the, does anyone remember what it was called? To multiply top and bottom by the conjugate. So you'd have to multiply the top and the bottom by 4 plus 5i. And what that does is it gets rid of all the i's in the bottom. All right. So we've done it that way, but we're going to come up with a better way to multiply and divide. And even better, I'm not sure if we're going to get to this part today, but if you wanted to do this, that means you'd have to write 3 plus 6i 5 times in parentheses, and then FOIL every one of them. So that's going to take a while. That's still doable, but it would take a while. Now, if I ask you to do that, that's not really doable. Not with foiling, because you'd have to write 50 sets of 3 plus 6i, FOIL each one of them, and then it's just going to be hundreds and hundreds of multiplications and additions. So there's a much easier way, whether you ask me to do this problem, or that problem. I can do either one just as quick, as long as I know how to write complex numbers in trig form. Okay? So that's some of the advantages. So multiplying, dividing, I think we'll get to today. Raising to powers might do, that's still pretty straightforward. Then when we get into roots, that's a little trickier. And that's in 8.4. Okay, so just a reminder what a complex number looks like. Okay. It has a real part and an imaginary part. And I'm going to show you, I don't think we've done it before, how you can represent a complex number graphically. Okay. Not even changing it to trig form yet. We're just going to leave it as like 6 plus 5i or whatever it is. And I'm just going to show you how to graph it. So basically when you want to graph a complex number, it's just looking at the real and imaginary part and putting them into a coordinate. All right, so graphing complex numbers, this is your real, and that's kind of like what would be on the x-axis, but we don't call it the x-axis, we call it the real axis. And this part is your imaginary, and that's the up and down. That's what we used to call the y-axis. And I got a picture of that right here. So your real axis takes the place of the x value. Your imaginary axis is now taking the place of the y. And that's called the complex plane. We can't really do this on a graphing calculator. There's no mode for this kind of thing, but it's very, very easy to do by hand. So we'll look at a couple examples of just graphing numbers in the complex plane. Does everyone have the diagram of it? Okay, one mistake I see a lot is people switch the names. Well, if you switch the names, it's almost like if you graph the coordinate 5, 3 and then 3, 5. They're not the same. So you got to make sure we've got those names correct. Okay, so let's graph these points. So -4 minus 2i. Okay, Gabe, in that first coordinate, what's the real part?
The -4.
-4. And the real axis goes which way?
The real axis goes vertical. I mean, horizontal.
Horizontal, yeah. Real axis is horizontal, and we're going to go -4 units. So we're going to start 1, 2, 3, 4 units to the left. And Natalie, what's the imaginary part of that coordinate?
-2.
-2. And the imaginary axis goes which way?
Vertical.
Vertical. So we're going to go down 2. So 1, 2, 3, 4, down 2. And that's all you have to do to graph the point -4 minus 2i. So we're going to do a couple things before we start doing trig form. Very simple things like this. But then I'll let you know when we start getting into trig form. Okay. -2 plus 3i. Chris, what's the real part there?
-2
And the imaginary part?
plus 3i. Or 3i.
Just 3.
Oh.
Yep, so real imaginary part plus 3. Real part, -2. So starting at the origin, how would I graph that point?
You would go left 2, and then down up 3.
Left 2, up 3, and that's the point, -2 plus 3i. Okay, 5i. Kaylee, what's the real part in 5i?
There isn't one.
There isn't one.
0.
So it's 0. What's the imaginary part?
5.
5. So how would I graph that point starting from the origin?
Just go up 5.
Up 5. That's it. So 1, 2, 3, 4, 5. And 6. Okay, Madison, what's the real part in 6?
6.
6. Imaginary part?
0.
0. So it's like we're graphing 6, 0. Just 6 units to the right. 1, 2, 3, 4, 5, 6. And that's it. Any questions on graphing complex numbers that are in that form? Okay, now the reason we're looking at that is because eventually we're going to get into finding this distance right there. What did I just draw? I drew in kind of like a dotted line. But where did I draw it to? From the point to the origin. So the origin is like the two-dimensional version of 0, right? If you had a number line is 1 dimension, 0. So I drew that basically to 0. What do you call that if you measure the distance from a spot to 0? There's a name for that. The distance from that coordinate to 0. Yeah. Not the slope of it, but
The absolute value.
it's the absolute value. So we're going to look at how do you find the absolute value of a complex number. It's easy. Just find the length of that line segment that I just drew, basically by making a right triangle and using Pythagorean theorem. So that's what we're going to look at next. So remember, absolute value is just the distance from 0. Or if you want to talk two-dimensional, it's the distance from the origin. So this is your complex number. A is the real part. B is the imaginary part. Absolute value of that black point is that distance that I just drew in red. I think I just said it, but if you know A and B, how could you find the length of the line segment in red? Yeah, you just use the Pythagorean theorem, which means you square A, you square B, you add them up, and then you take the square root. That's exactly what this is. It's a Pythagorean theorem. A squared plus B squared, and then take the square root of it. So you don't have to know a new formula or anything like that. It's just using something you already know how to do. Finding the hypotenuse in a right triangle. Now, the only time you don't really have to do the formula is if you've got a point right on the axis. Okay. Like 6. Well, if you wanted to know the absolute value of this, which is really 6 plus 0i, it's just 6. You can just count because it's straight. Okay. Same thing here. 0 plus 5i, it's just 5. Right? You don't really need Pythagorean theorem for that. But the formula still works. Okay. If you want to still use it, it'll work fine. Okay. So let's find the absolute value of 3 plus 4i. Okay. So using 3 for A, 4 for B. Anyone think they can give me the expression I'm going to set up to find the absolute value? Yep.
Square root of 3 squared plus the square root of 4i squared. Wait,
Close.
4 squared.
Just the 4 squared. Yep. So if you think of the 3 and the 4 as the sides of your triangle, the legs, you're finding the hypotenuse. Okay. So 3 squared plus 4 squared is going to give me the square root of, yep, please. 25. Which means that the absolute value of 3 plus 4i is 5. It could come out to a square root. Okay. If you get a square root, make sure you always reduce it as much as you can. Like square root of 20. I would expect to see something like that as, what would that be? 2 square roots of 5. Okay. Any questions on that? Also, be careful if one of these numbers was negative. If that was a negative 3, and you changed the problem, what would the absolute value be now? Same thing. It doesn't matter if one of the sides is negative or anything like that, because when you square the negative, it goes away. So the absolute value there is still 5. All right, so I'm going to show you one way we can add complex numbers, just kind of by looking at it visually. Right? And then after we do that, that's the last thing we're going to do, writing numbers like this, and then we'll get into writing them in trig form. So remember, when you add or subtract complex numbers, the idea is basically to combine like terms. Okay? We already have a pretty efficient way of doing it. I'm just showing you visually how combining like terms works if you were to draw it out. Okay. So I've got 2 complex numbers. One of them has the coordinate AB, the other one CD. Each one of those complex numbers has a real part, that's the A and the C, and an imaginary part. That's the B and the D. So when you want to add these complex numbers together, there's a couple different ways you can think about it visually. Okay. Let me draw in triangle here and here. Just to color code it, it's a little crooked, but whatever. That's the real part of the triangle that's standing up tall. That's basically C. There's the real part of the triangle that's laying down. That's A. Okay. I had to do them in different colors because you wouldn't really see them if they were right on top of each other. Red is going to represent the imaginary part here and the imaginary part here. So if you wanted to add those 2 things together visually, remember, all you got to do is combine real parts with real parts, imaginary with imaginary. So here's your first real part, right there. Here's your second real part, right there. We're just adding them together. Here's 2 things grouped together. Here's my first imaginary part. That's D. Here's the other imaginary part I drew. That's B. So once I stack all these together, wherever I end up, that right there is the answer. Just combining the real parts together and the imaginary parts together. So that coordinate is now A plus C, comma, B plus D. I think if you want to be technical about it, I did D plus B, but B plus D, D plus B, it's like 2 plus 3, 3 plus 2. It doesn't matter. And I think I write that right here. So the complex numbers Z1 plus Z2, that's Z1, that's Z2, can be represented by the coordinate A plus C. Add the real parts together, B plus D. Combine the imaginary parts together. And that's what it would look like visually. Visually, it's kind of a slow way to do it, but it's just kind of a way when you're first learning complex numbers to kind of understand how it would look if you did it visually. So let's try the same thing here. We got 3 plus 5i. That's the first point. That'll be in black. And the second point, I'll do in green. 2 plus I. Now, this is a little different because it's got a negative in front. What do you think I might want to do first here? Yeah? Yeah, so let's think of the problem this way. That's fine. 3 plus 5i plus. What would the other coordinate be if I write it as a plus?
Negative 2 minus I.
Yeah. Now we can do this exactly like I just showed you in the other problem. So graph negative 2 minus I. So negative 2 minus I. And let's draw our triangles. Left 2. And I'm stopping between each one because I want each piece to be kind of separate. So left 2, down 1. And then right 3, up 5. Right 3, up 5. You don't even really need to draw in the hypotenuse. Okay. So let's just take all our real parts. It's all the horizontal stuff. I'll put it there. All the imaginaries. That's my vertical stuff. And just stack them all together starting from the origin. So real part plus real part. Imaginary part plus imaginary part. And we end up right there. Wait a minute. Did I add that the wrong way? Let me put those back the way they were. One of those they were supposed to be negative. So what I should do, I should have put an arrow to point. This one is actually going left, and that one's going down. I think I put them as all as going right, which we don't want to do. All right, so let's try that again. All right. So I don't know what that is. All right, that's a positive 3. That goes with that. That's a positive 5. That goes with that. This was my negative 2. That goes with that one. This was my negative 1. That goes with that one. So I'm just going to try to remember which one goes where. So this one goes to the right. This one goes left 2. So putting it on the end, it actually brings me back 2 units. It's hard to see, but now I'm right there. Okay. Then we're going to go up 5. That's the positive 5. And then on the end of that, this one brings me down 1. So I actually end up right there. let's see if that makes sense. 3 minus 2 gives me -1. 5i minus 1i gives me 4i. Can't do math today. 3 minus 2 is +1. 5 minus 1 is still 4. So 1, 4 is where I should have ended up. 1, 4. Yeah, so that's where I ended up. So it's just, the book just shows that. It's just kind of a different way of thinking about adding complex numbers, but looking at it visually. It's almost like adding vectors. When we get into vectors, we're going to kind of do stuff like that. Right? But it's kind of weird when a vector, when it goes backwards, because then it's like on top of itself and you can't really see it. Okay. Honestly, most useful thing? Probably not. But just a different way to think about adding and subtracting complex numbers. Any questions on that idea? Works a lot better when everything is positive because then you don't trace back over yourself. But it's not a huge deal. Okay, so now from this point forward, the rest of the week, we're going to look at how to write numbers in trig form. So first thing we're going to learn is how do we take a number that's not in trig form and get it in trig form. Then we can do stuff with it. Okay. All right. I'll just leave that. All right. So what I've drawn here is a coordinate, and I switched to using x and y to represent the real and imaginary part, just to kind of make the connection in your head. X is the real, y is the imaginary. I mean, you can still use a and b if you want. Now, when you write a number in trig form, you don't have an x and a y anymore. What you have instead is an r and a theta. All right? So let's figure out how we can write this in trig form. So what we have to do is get rid of the x and get rid of the y. Let's start with the x. We have an angle here. We have x here. We have r there. We'll do y after. From the perspective of theta, what's the name of the side in this triangle that I've labeled x? Adjacent. And what's the name of the side in the triangle that I labeled r? Hypotenuse. Which trig function has adjacent and hypotenuse? Cosine. So let's write a formula. Cosine of this angle equals the length of the real part, which I'm calling x, over, technically it's over the absolute value of the coordinate, but I'm just shortening that to r. Okay. Now let's get x by itself. What would x equal? Yeah. Well, not quite, because r is already divided.
And then multiply.
Multiplying, yeah. So r cosine theta. So when you write something in trig form, the goal is to get rid of this and this. That's just how it works. Well, we've got a way to get rid of x. We can replace it with a formula. Now, let's look at this. Same angle, same hypotenuse, except now I'm going to use y. So focus on what's in red. So we know r is the hypotenuse. What's y?
Opposite.
Opposite. Which trig function has opposite and hypotenuse in it? Sine. So we can set up a formula for sine. Opposite over hypotenuse. And how do we get, what would the formula be for y? Rob?
R times sine.
r times sine of theta. So anytime we write something in trig form, we have two things. R, which is a distance, and if you're wondering why I'm calling it r, it's because a lot of times people think of that point as being on a circle. It's like the radius of a circle. So r is a number we use, and theta is an angle that we use. So those are the two things you have to use to write a number in trig form. A radius and an angle. And we just came up with the formulas right here. So now, take this, and don't draw circles. Let's try, take this, fill that in for x, fill that in for y, and that's going to give you the trig form of a complex number, what it looks like. So if you do that, the first thing you get is instead of x, r cosine theta, plus the I just stays right where it is, but then the y turns into r sine theta. Now, the first term and the second term that I just underlined, they both have what in common in front of the trig function? They both have an r in common. What can you do when you have two terms and they have the same thing in common? Yeah, you can factor it out. Take out that common factor. So if you take out the common factor, you're left with an r on the outside of parentheses, cosine theta, plus I sine theta. And that is the trig form of a complex number. So what would it actually look like if you had a number in trig form? Something like this. 5 cosine 10 plus I sine 10. That's exactly what a final answer would look like if you wrote a complex number in trig form. The only thing that you have to figure out is r, which pretty much already know how to do because it's just the absolute value of the coordinate. So that's like a radius. And then we have to find theta. So we have to figure out how do we get theta. So that's what I just said. So to use this form, you have to find r and theta. So r, distance from the origin. Theta is the angle with the positive x-axis. So it's the angle from here, however far you go. It depends on which quadrant your coordinates in. All right, so how do you think we would get theta? If you had a point somewhere up here, you can do your Pythagorean theorem to get that. That's your radius. But how would you get theta, given that you're going to know this and you're going to know that? Yep. You're going to need a trig function. Yep. Which trig function would you need?
Sine.
Well, sine would involve the hypotenuse, which you might know, but that's something you're going to calculate. So I would stick to the information that they give you, which will be the x and the y. Yeah?
Tangent?
Tangent, yes. So if you use the tangent of theta, tangent is opposite over adjacent, and I'm going to write this nicer on the next page, then we can get theta by itself by doing what on both sides? Emily? Yeah, we could do inverse tangent on both sides, and then we'd have our angle. So that's how you get your angle. You use inverse tangent. How do you get your radius? Pythagorean theorem. Right, so I'm not going to draw out that whole picture again because I really just drew it.
Can we go back?
And again, I'm going to write this down very nicely in steps in a second. So to find your radius, or to find your r, use the Pythagorean theorem. Now, to find your angle, I said that we're going to use tangent, or more specifically, inverse tangent. Well, if you remember when we studied inverse tangent always gives you an answer between -90 and 90. Always. It'll never give you an answer outside of that. So, if inverse tangent is always going to give me an angle from -90 to 90, which quadrants does that mean my answer would always be in? What is it?
I said 1.
1, yeah. Where else? 4. Inverse tangent by itself will only give you an answer in quadrants 1 and 4. So that works great if you're graphing a point that's somewhere over here or down here. Basically, it works whenever your x value is positive. Okay. If you're graphing the point like, you could find that angle no problem. Just do the inverse tangent of y over x, because that's in quadrant 1. If you had something like this, perfect. You can find that point because that's in quadrant 4. But if x was negative, you would end up over here. An inverse tangent will never give you an answer over there. So you've got these answers over here. That's like half the quadrant, or half the plane. If you want to get to quadrants 2 and 3, you basically have to add 180 to your answer. So if you've got a point like this, and they say to write it in polar, or write it in trig form, this is in quadrant 2. So to find your angle, you're going to take pi plus the inverse tangent of y over x, or if you're doing it in degrees, what would you use instead of pi? 180. Yep. Okay, so the only time you've got to add 180 to the calculation is if your point is in quadrants 2 and 3. How would you know that? Well, I just showed you guys earlier how to graph complex numbers. So you just graph it and look, or even you don't even have to graph it. Just kind of look at whether x and y are positive and negative, and then you'll know your quadrant. Now, if a point is on an axis, we can run into some weird things using this formula, especially if the x value was 0. Because then you're trying to do the inverse tangent of something divided by 0. You can't do that. So we don't use these formulas when you're on a quadrant. You use them when you're on an axis. You only use these formulas when you're actually inside a quadrant. If you're on an axis, your angle is going to be one of these 4 answers: 0, 90, 180, or 270. Now, if you've got a coordinate that's on an axis, how can you tell that very quickly? Just by looking at a coordinate, you could say, yep, it's on an axis. What always happens? Yep.
The coordinate is 0.
Yeah, one of the values in the coordinate will be 0. And we graphed a couple like that as well. Okay, so just remember 0, 90, 180, 270. Or the values are in radians if that's how you're doing it. Okay, so let's find the trig form of this number. Okay, there's 2 things you have to find. You've got to find r, and you've got to find theta. Doesn't really matter which one you do first, because you're not going to use one to find the other. So Nate, which one do you want to do first?
-2.
I
don't really know.
that is not an option.
Was.
So do you want to find r first or theta first?
R.
Okay, how do I find r?
You use Pythagorean theorem.
Exactly. So if you want to sketch it, you don't really need to, but if you wanted to, left 2, up 2. So it's kind of like right there. 2, 2, and you're using the Pythagorean theorem to get your radius. So r squared, Kaya, can you finish what would go on the other side of that equal sign for me?
2 squared plus 2.
And can you say it one more time?
2 squared plus 2.
Yeah, I mean, you can do 2 squared because the negative is going to cancel out anyway, but that negative is going to be important when we find the angle. So we don't want to forget about it for everything. I mean, if you skipped it here, it'd be okay. But in general, I would always put the negative in, and then if the formula gets rid of it, that's fine. So r squared equals 8. So that would mean r would equal what if we fully simplify it? Yeah.
2 square roots.
Yeah, exactly. 2 square roots of 2. Okay, so we've got r. Kathleen, what else do I have to find? Theta. And what quadrant am I in? Because that's going to control what formula I use for theta. I'm in quadrant 2. So, Chris, when I'm in quadrant 2, is that a quadrant where I have to add 180 or no?
No. Yes.
Sure.
I'm not sure. I don't know why.
So which one is it? Do we add 180 or do we not add 180? Gabe?
Yeah.
Yes, you do. If you're in quadrant 2, you have to add 180. Okay? So what we're going to find now is this angle right there. So it's inverse tangent of y over x. Let's do that. It's theta. Inverse tangent. And now the negative is important. Y over x. So 2 over negative 2. And if you just do that, you're going to get an answer in quadrant 4. That's not what you want. That's going to come out to negative 45 degrees. If you add 180, that's going to cause it to come out to 135. If you don't know that, you could just type that in and that's what you'll get. So there's your angle, 135. Now, write the final answer. Final answer should look just like that. Just fill in what we got for r, fill in what we got for theta, and stop. Don't do anything else. All right, so we got r. You know what? I'm just going to move it over a little bit. Cosine theta, which was 135, plus I sine 135. And that's the final answer for how you write that in trig form. Now, if you were to take the 2 root 2 and distribute it out and do out all the arithmetic, you would be changing it right back to what we started with. So on your calculator, if you type in 2 root 2 times cosine 135, you're going to get negative 2. And if you type in 2 root 2 times sine 135, you're going to get positive 2. Okay. So we don't want to change it back. That's why we just leave it like that. Okay. So any questions on how we change this number from what we call rectangular form to trig form? It really, it's not really doing anything using formulas you didn't already know. We already knew inverse tangent. We already knew Pythagorean theorem. We're just using the formulas in a way we haven't before. All right, so last thing we'll look at today, basically from here out, we're going to do four operations with trig form of complex numbers. We're going to multiply, divide, raise to powers, and take roots. Taking roots is the hardest one. Multiplying and dividing is very simple. So is powers. Very simple. All right. So, quick reminder of the old way you would have to do this. If you wanted to divide two complex numbers, and this one isn't even as bad because it's not a complex number in the top with an imaginary part, it's just a pure real number. What would you have to multiply top and bottom by here if you were going to do this out?
5 minus I.
Yep, 5 minus I. So let me go through that, just doing it like if I was doing it at my normal speed. So I would distribute that out in the top. Now in the bottom, that's going to be a FOIL, but I'm foiling conjugates, so I know that the outer terms, which is 5 times negative I, and the inner, 5 times positive I, they're going to cancel. So I don't need them. So all I really have to do is 5 times 5, positive I times negative I. Okay. I squared is negative 1. So the bottom becomes 25 minus 1, or 26. Now I have this in the top. And now to write it in standard rectangular form, I have to separate it into two fractions. 15 over 26 minus 3 over 26. And we put the I out front like that. Okay. Not that bad, but still, we can do this a lot faster, especially if the numbers were already in trig form. Would it be faster to use trig form in this problem? No, because I would have to change this to trig form, change this to trig form. And that's going to be more work than to just do it this way. So the advantage comes in when the numbers are already in trig form for you. Okay. All right. So let's say we have two complex numbers. Each complex number is going to have its own radius and its own angle. So when we do an actual problem, it'll be set up like this. I'll give you a radius, I'll give you an angle. I'll give you a radius, I'll give you an angle. These angles just happen to be in radians, but it doesn't matter. If you want to multiply the two complex numbers together, instead of doing all the foiling that we used to have to do, and remembering that I squared is negative 1, you only have to do two calculations. You multiply R1 times R2. So you multiply the two radii together. And then you take theta 1 and theta 2 and you add them together. And that's your new angle. That's all you have to do to multiply two complex numbers. Multiply the radii, which that's a very easy calculation. There's no FOIL. Add two angles together. Another very easy calculation. And that takes the place of having to do all the foiling stuff. Now, dividing two complex numbers is a very, very similar formula. Does anyone have a guess if we were going to divide Z1 and Z2, what we would put right after the equal sign? Yep. Yep. So the shortcut I'm showing you now is going to take the place of all the stuff I just did. Multiplying by the conjugate, foiling it out, changing I squared to negative 1, putting it in two fractions. All that stuff's going to go away with this formula. You do two calculations. Divide your radii. And what do you think you're going to do with your angles this time? Subtract them. Yes. You're going to subtract them. Now, the only thing that couldn't happen is you couldn't have R2 be 0 because then you'd be dividing by 0. That's a problem. So R2 would never be 0. Right? But divide your radii, subtract your angles, and that takes the place of all the stuff I just explained with how we used to have to divide complex numbers. So this saves you a little bit of time, but tomorrow you're going to see where it could save hours if you had a power. Okay, powers can be really hard. Very simple though when you do it this way. Okay, let's look at an example. So just to save a little time, what I did is I already converted the two numbers for us. We actually did this one, -2 plus 2i. There's your radius, 2 root 2. And we had an angle of 135. Well, I just wrote it in radians. So if you take 135 and multiply by pi, all right, I'm just going to get another calculator. If you take 135, multiply by pi, and divide by 180, that's where the 2.36 is coming from. That's all it is. It's 135 in radians. So we already did Z2 ourselves by hand. We didn't do, I think we found the absolute value of a number like this, so we knew the radius was 5. I don't think we found the angle. It comes out to 0.93 radians. Now, if you had to find that 0.93 by hand, is this a coordinate where you would add pi to the inverse tangent? No. That's in quadrant 1. You would just do inverse tangent of 4/3, and that's how you'd get 0.93. Okay. So let's multiply those and divide them. Okay. Let's start with multiplying. When I want to multiply them together, what do I do with my radii? Yep, yeah. Multiply them. What's 5 times 2 root 2? We'll just leave it as an exact answer, not a decimal.
10 root 2.
10 root 2, yep. So 10 root 2. I mean, it's kind of weird. Usually if you have some decimals in the problem, you don't usually mix like exact things with decimals, but it's fine. Cosine. And now what do I do to get my final angle? Robin?
You add the two thetas together.
Yep. 0.93 plus 2.36, and we're done. 3.29. Now, if somebody really wanted this back in rectangular form and they said, you know what, I don't want you to leave the answer in polar, well, it wouldn't be that hard. I would just take on my calculator 10 root 2 times cosine of 3.29. That's the real part. And then 10 root 2 times the sine of 3.29. I would just distribute it out, and I would have my answer the way we were used to doing it. But they didn't say, they just said leave in trig form. So we don't have to do that. Okay. All right, so now let's do Z1 divided by Z2. So Jacob, to do Z1 divided by Z2, what do I do with my radii?
I am not sure.
All right. Do you write it down? Do you have the formulas?
No, I don't.
Yeah.
You divide the R1 by the R2, so it would be 5 divided by 2 square root of 2.
Just take your two radii and just divide them. So I'm going to do it off to the side because I'm going to end up with a square root in the bottom. And we don't want to leave that like that. So 5 divided by 2 root 2. Multiply top and bottom by root 2. And what do I get for a radius?
5 root 2 over 4.
Yes. So there's my radius. Cosine of, and now what do I do to get my angle? Yep.
Subtract the thetas.
Subtract the thetas. Now, something's going to happen here. Minus 2.36. So I get negative 1.43. Plus I sine negative 1.43. Now, there's nothing you can really do with the radius. I mean, unless you want it as a decimal. But there's two ways to get rid of the negative in front of the 1.43. What can you do to an angle to make it positive? Yeah?
Times it by the negative.
Well, you can add or subtract something. You can't multiply it by something, but we can add or subtract something to an angle. Yeah?
360.
You could add 360, or in this case, what would you have to add? Yep.
2 pi.
2 pi. So that's one way, if they say do not leave negatives in the answer, that's one way to get rid of it. So plus 6.28, and that would give you 4.85. So that's another acceptable answer. The other way you can get rid of the negative without making the number bigger, I'll tell you in a second.
Where'd you get the 6.28?
That's 2 pi. That's adding 1 revolution to the angle. Just like adding 360.
Okay.
So you can always add or subtract 360 and get the same thing. The second way to get rid of negatives is a little tricky, but we have talked about it briefly once. Yep.
And you just multiply everything by -1.
No, we can't multiply everything by -1. If you could, that would also get rid of the negative. But my hint is, let's just take a look at the cosine of, I'm just going to make up a number, 48, and the cosine of -48. What's the difference between those two answers? They're the same thing. When you have a negative with a cosine, the negative doesn't matter. You could just forget about it. It doesn't make a difference. And that's because of when you graph, you could look at the symmetry of the cosine function. But we don't really have to get into it. So the negative, you can just get rid of. Now let's try it with sine. If we take the sine of 75, we get that, and the sine of -75. Are those the same thing?
Wait, no. No, they're not.
They're not, but there is a connection between them.
They're the same numbers, it's just one's positive and one's negative.
Yeah, they're just opposites. So what you can do is you can put the negative in front. So the sine of -75 is the same as the negative sine of 75. So you can take the negative and move it to the front. You can take the negative and move it to the front. Okay, so all of these answers are correct. The first way had a negative for the angle, and the second and the third way got rid of the negative 2 different ways. There's not really a preferred way. I mean, a lot of people do it the second way. They just add 2 pi.
Where's the I in the last
Oh,
column?
I didn't forget the pi. Thank you. Yeah, you need that. Any question on that? So you don't have to worry about the negative if that doesn't come up. It doesn't always come up. Sometimes it does. This was just another one practicing multiplying and dividing. I don't think we need to really go through it. This one would take a little longer because you don't have your R and your theta, so you'd have to convert these to trig form first, and then you could do it. All right. But for now, I'm gonna hold off on that one. All right. So homework tonight, it's on page 450. And it's 1 through 3, 5, 8, 10, 11 to 15, 17 to 21, and then 33, 34, 37, 47. So we've looked at 2 things you can do with trig form of complex numbers, multiply and divide. Tomorrow we're going to look at how you can raise to powers, very simple, and how you can take roots, not as simple. There's a method to it, it's a little cumbersome to go through, but we'll go through it.